All right, fluid flux across the capillary. Now, we already know one of the factors that moves water is osmosis. Well, the second factor that will move water are hydrostatic pressure differences. So we're going to have two fundamental forces at work that are going to influence water flux across the capillary. All right, first off, number one, we have to have definitions. Definitions. Page 10, page 7. Yeah, let me back up. There's more solute loss than water. Gawiska. Okay? More solute loss than water. All right, we have to have definitions here. Here we go. In green, we're going to bring in, we're going to put a plus. This will be filtration. Filtration means fluid coming out of the capillary to the interstitium. Absorption, we're going to bring in yellow. We'll put a negative. You'll see why. Absorption means water movement from the interstitium back into the capillary. So if it's leaving, filtration. If it's coming in, it's absorption. Those are basic definitions that we have to work with. And again, for filtration, we'll put pluses and then put them in green. And for absorption, we'll put minuses and have them in yellow. Two things make water move. Hydrostatic pressure differences, high pressure to low pressure, and osmotic forces. But we're going to call them oncotic. Oncotic just means osmotic. That's all it means. All right, here we go. We're going to start first with the hydrostatic pressure in the capillary. This is a force promoting filtration. So, again, water moves based on pressure gradients. The higher the pressure gradient, the greater the water will flow. So the hydrostatic pressure in the capillary is that force tending to promote filtration. We're going to have three things that are going to influence hydrostatic pressure in the capillary. First, it's going to be directly related to the flow. And as we will discuss at a later date, the flow to this capillary is regulated at the arteriole. But bottom line, if flow goes up, hydrostatic pressure in the capillary goes up, which promotes filtration. Second, venous pressure. If venous pressure goes up, capillary pressure goes up. In fact, I want you to just tie those together. Every time you think, every time I say, every time you hear venous pressure, I want it to be like a Pavlovian reaction. You go capillary pressure. So when you hear venous pressure, you just go capillary pressure, capillary pressure. You got to put those two together. Be like, Pavlovian reaction. So venous pressure, capillary pressure. There we go. Yes, just put them together. That venous pressure goes up, capillary pressure goes up immediately. And that's a very important high yield thing to remember. You'll see we'll bring it in several times. All right, because if capillary pressure goes up, that promotes filtration. It promotes filtration. Third factor that will influence hydrostatic pressure in the capillary, directly related, will be blood volume. Now, hopefully that makes sense. Okay? Because pressure, volume, they're directly related. The greater the volume, the greater the pressure. All right, so those are going to be our three things. That's going to be part of our core. We need to know those three things, and we'll just apply again and again. Now, next factor will be the oncotic force in the interstitium. There's not a lot of proteins there, but nonetheless, there are some. So they will exert an osmotic force, which will promote filtration. So oncotic, the oncotic forces in the interstitium are tending to pull fluid forward. So we're going to have two forces for filtration: hydrostatic pressure in the capillary and oncotic pressure in the interstitium. All right, now how about forces for absorption? Well, the first is the osmotic force in the capillary. In other words, the oncotic force in the capillary. What was my effective osmol? Oh, Miguel, man, you're fast. You must have been reading my mind. Good job. All right. This is the effective osmoles in the vasculature promoting absorption. Those are the plasma proteins, the most abundant being albumin. Okay? Sodium not here. It's not an effective osmol for the vascular space. It is for extracellular, but not vascular. Okay? So the oncotic force here will be directly related to the proteins because that's the solute exerting the osmotic force. That's the effective osmol for the vascular space. Hydrostatic pressure in the interstitium will promote absorption as well. Remember, the hydrostatic pressure is pushing the fluid. So hydrostatic pressure in the interstitium promotes absorption. So we have two forces for filtration, two forces for absorption. And again, for the filtration, we put pluses. For the absorption, we put minuses so that we can work with numbers. There's our fundamentals. Okay? Forces for filtration get a plus. I drew them in green. Forces for absorption get a minus. I drew them in yellow. Those are our four fundamental forces influencing fluid flux across the capillary. And it is the interplay between those that determines whether or not we are filtering or absorbing. If the forces favor absorption, then there's water movement from the interstitium to the vascular space. If, on the other hand, the forces favor filtration, in other words, these two forces are greater than those two forces, then fluid's going to leave and we'll have net filtration. That's how it works. That's how it works. And that's why we need to know these fundamental forces and what impacts them. All right. All of that put together is what's referred to as the Starling equation. Starling equation defines fluid filtration. Now I know every one of you love mathematics. You love equations. So you just love me to put equations up there. Nobody out there just doesn't want to do math. Nobody wants, everybody wants equations. I know. Oh, no? No? Oh, okay. All right. So do you have to memorize this equation for step one? No, not at all. Not at all. Okay? You do need to know these players, just like we had. If you understand those players, I'll show you how I can do a real quick calculation. Okay? Where you don't have to worry about, a long formula. But we do need to bring in a concept. And that is, the Starling equation includes this coefficient. Bottom line, this coefficient is telling you about permeability of the capillary. That's all you got to worry about. You won't have to calculate a QF on step one. But do know, the greater the capillary permeability, the more likely you're going to have filtration. So if I increase capillary permeability, I'm going to promote filtration. All right? That's what you need to know for step one. You don't have to do the entire equation. But I'll show you how I can very easily quantitate these fundamental forces. Just remember, absorptive get negative, filtration get positive. Okay? Now, an important thing to remember, do not forget the lymphatics. The lymphatics' job, regulate interstitial fluid volume. So they're going to impact hydrostatic pressure and impact the oncotic forces in the interstitium. Their job, lymphatics' job, regulate interstitial fluid volume. All right? Regulate interstitial fluid volume. They will decrease interstitial fluid volume. They take the fluid away. So if the volume in the interstitium goes up, the pressure goes up, that drives lymph flow. Their job, do not forget the lymphatics. Their job, regulate interstitial fluid volume and protein content. So if protein starts sneaking in here, the lymphatics can kind of pull them away. Atandra, you're absolutely right. Bradykinin is one of those examples that increase permeability. It increases permeability. Yep, we'll go into the edemas in just a second. All right, what? A bug? This is physiology. What's up with that? This is a bug. What are we doing with y'all had microbiology, so why am I bringing in this? Why am I bringing in this? Oh, very good. Yeah, this is the filaria that blocks lymphatics and results in massive edema. All right, that's called elephantitis. Common name is elephantitis. But this is a quick little reminder of the filaria that causes it. Every once in a while, we even bring in a bug. Oh, a bug in physiology. Smash it. All right, so those are our forces. Let's work with them. Here we go. I'll show you how to work with it very, very quickly. Pressure in the capillary, hydrostatic pressure. Does it get a plus or a minus? Does it get a plus or a minus? Does this get a plus or a minus? Is it promoting filtration, a plus? Yep, very good. How about this one? Pressure in the interstitium, does that get a minus or a plus? Gets a minus? See how easy it is to work with this? Oncotic in the capillary, what does that get? Minus or a plus? Oncotic in the capillary, minus or a plus? It gets a minus. Good. Oncotic in the capillary is promoting absorption, so it gets a minus. Oncotic in the interstitium gets a plus because it's promoting filtration. So I just take my two numbers that have a plus, add them together. My two numbers that have a minus, add them together, and then subtract absorption from filtration. And I have just quantitated the net forces. See how simple that is? Nice and easy. Nice and easy. As long as we can remember what promotes filtration, what promotes absorption. And we can quantitate. All right, it's a plus, so that means it is favoring filtration. If it becomes a minus, then it's favoring absorption. Then it's favoring absorption.